All right, welcome back to the deep dive. If you've been with us for a while now, we've been taking a pretty deep look at the OEIS, and some of those entries out there, they really grab your attention. Today, we're going to dive into one of those ED A00172, the Franel numbers.
Yeah, it's a really great sequence. Anyone out there listening who's seriously following along with us and going deeper into number theory, well, you're going to find a lot to like with Franel numbers. They seem simple enough when you first see them, but wow, there's just so much there.
So let's start there then. What exactly are these Franel numbers? How are they defined?
Yeah, so they're also sometimes called the third order Franel numbers, just to be specific, and they're defined using a sum. Pretty straightforward at first glance. We write the nth Franel number as a of n, and it's just the sum of the cubes of the binomial coefficients.
Cubes of binomial coefficients. Okay, so we're cubing those and then adding them all up.
Right, exactly. And the lower index in that sum, that goes from 0 up to n.
So could we write that out formally?
Yeah, so formally we write it as a of n equals, and then we use the summation symbol with k equals 0 at the bottom and n at the top of open parenthesis, n choose k, close parenthesis, all cubed.
Okay, so n choose k, all cubed, and then add all those up from k equals 0 to n.
Exactly.
Got it. So what are some of the first few terms of the sequence?
Sure. So if we start with n equals 0, the first few terms are 1, 2, 10, 5, 6, 3, 46, 22, 52. It keeps going from there, and the numbers start to get really big pretty fast. The OEIS entry has a lot more terms listed out, but as you can see, they really take off.
Yeah, wow, they do get large quickly. So in our deep dive today, what's the big question we're trying to answer about these numbers? What's so special about them?
Well, the interesting thing about Franel numbers is they show up in a ton of different areas of math. I mean, the definition is really simple, right? But we find them in combinatorics, number theory, analysis, even geometry. So we're going to take a look at some of these places where they pop up and try to figure out why they're so important to mathematicians.
It sounds like we have a pretty interesting journey ahead of us. So we've talked about how they are defined. Let's start in an area where it seems like they have a natural connection, combinatorics. The art of counting and arranging things. The OEIS entry mentions something called Strell's identity.
Strell's identity is really interesting. It gives us another way to write the Franel numbers, and it's kind of surprising when you first see it. It says that a of n, that nth Franel number, it's also equal to the sum from k equals 0 to n of, well, we have a square of a binomial coefficient here, so open parenthesis, n choose k, close parenthesis, squared times another binomial coefficient, open parenthesis, 2k, choose n, close parenthesis.
Wow, that's pretty interesting. So you're saying that adding up the cubes of the binomial coefficients gives us the same exact sequence as this other sum with squares of binomial coefficients and a different binomial coefficient term. It seems like there has to be some kind of connection between those two, like maybe we can prove that they are the same using a combinatorial argument.
Exactly. That's what we often find in combinatorics. When we have two different ways to count something, there's often a deeper meaning behind it. It would be really interesting to find a direct way to connect those two sums, but that's still an open problem.
So maybe one of our listeners out there can take a crack at that.
Maybe.
So sticking with this combinatorics theme, the OEIS entry also mentions a connection to something called Nash equilibria.
Yeah, Nash equilibria. So that's a concept from game theory. It turns out that the nth Franel number, a of n, it tells us something about games with 3 players. Specifically, it gives us the largest possible number of totally mixed Nash equilibria when each of the players has n+1 pure strategies.
Okay, now how is that possible? How can a sum of binomial coefficients tell us something about strategies in a game?
Okay.
That seems like we're moving to a totally different area of math now.
Well, it turns out that when you're trying to figure out these Nash equilibria, you end up needing to solve systems of polynomial equations. And sometimes figuring out how many real solutions these equations have, well, it involves combinatorial stuff. And in this case, for this specific type of game, the number we end up with is a Franel number. It's pretty amazing, actually, how all these different areas of math connect together.
It really is. Now, I also noticed that the OEIS entry mentions something about directed path enumeration and semi-magic squares. What's that all about?
That's a really cool connection, but it's a little bit more specialized. The OEIS entry links to a paper on the Arcuve, which is a preprint server where mathematicians share their research. Basically, what's going on is that if you imagine a grid, like a checkerboard, and you try to count certain kinds of paths on that grid, and those paths have something to do with semi-magic squares, which are these special kinds of squares with numbers in them, well, it turns out that the number of those paths can be a Fresnel number.
Okay, so we're really seeing this theme of counting popping up again and again with Franel numbers. We can think of them as counting all sorts of different things, like paths or equilibria. Now, how about actually generating the sequence? The outline mentions something called recurrence relations, which I think are pretty cool, if I remember correctly.
Recurrence relations, they are really cool. They give us a way to calculate the next number in the sequence just using the ones that came before it. So we don't have to use that original sum every single time, which can be a huge time saver. For the Fresnel numbers, we have a second-order linear recurrence relation. It says that open parenthesis n plus 1 close parenthesis squared times a of n plus 1 equals open parenthesis 7 mean squared plus 7n plus 2 close parenthesis times a of n plus 8 man squared times a of n minus 1.
Okay, so that's quite a bit more complicated than just that simple sum, isn't it?
Yeah.
How do mathematicians figure out these kinds of relationships?
It often involves using tools from different parts of math, things like combinatorial identities, generating functions, or the theory of special functions. And it turns out that this guy, T.W. Cusick, he figured out a really general way to get these recurrence relations, not just for third-order Franel numbers, but for other Franel numbers too. There's actually a whole family of them.
A whole family of Franel numbers, wow. Okay, so now let's move over to number theory. I know from the outline that there's a connection between Franel numbers and prime numbers, which seems pretty cool.
It is really cool. A mathematician named Ziwei Sun, he proved this really amazing result that shows how Franel numbers and primes are connected. He showed that for any prime number p, if you take the pth Franel number, so a of p, and you divide it by p cubed, well, the remainder is always 2.
Really? Always two. That's a pretty precise relationship.
It is. And it's not at all obvious just by looking at the definition of Franel numbers. The proof uses some really clever ideas from number theory and combinatorics.
I remember reading that there's a conjecture out there related to this result, something by Gary Detlefs.
Yeah, Detlefs conjectured that the opposite is also true. So if you find a number, call it n, and if the nth Franel number, a of n, has a remainder of 2 when you divide it by n cubed, well then n has to be a prime number.
So basically a way to use Franel numbers to find prime numbers.
Exactly. But this is still a conjecture. It hasn't been proven yet. It would be a pretty amazing result if it turns out to be true, though.
That would definitely be huge.
Yeah.
Okay, now moving on, I see in the outline that Franel numbers are sometimes called Apery-like. What does that even mean?
Apery-like, yeah. That term is used to describe a bunch of different integer sequences that show up in number theory, especially when you're talking about this thing called the Riemann zeta function. Now, the most famous example of an Apery-like sequence is, well, the Apery sequence. A mathematician named Roger Apery used this sequence to prove that a certain value of the Riemann zeta function, zeta of 3, is irrational.
Okay, so kind of like Franel numbers, these Apery-like sequences have some pretty deep connections to number theory.
Yeah, exactly. And even though we don't have a strict definition for what it means to be Apery-like, we know that they usually have these linear recurrence relations with polynomial coefficients. And they often have combinatorial interpretations and connections to these things called modular forms.
So Franel numbers fit in with all these other important sequences in number theory. And the OEIS entry even lists a bunch of other examples of these Apery-like sequences, right?
Right. There's A0000984, the central binomial coefficients. There's A003893, which actually has a direct connection to Franel numbers through a convolution. There's A0002895, which is related to sums of squares of binomial coefficients, and a lot more. So the fact that Franel numbers are considered to be part of this group, well, it tells us that they're probably even more important than we might have first thought.
So we've talked about combinatorial stuff, number theory stuff, even a little bit about the structure of these sequences. Now let's talk about generating functions.
Generating functions, yeah, those are really powerful tools. They give us a way to study sequences using functions, and they can really help us understand the properties of a sequence. The OEIS entry gives a few different generating functions for the Franel numbers.
Okay, what do those look like?
Well, one form, it's for the ordinary generating function, which we'll call a of x, and it's given by, take a deep breath, the sum for n greater than or equal to 0 of open parenthesis 3n close parenthesis factorial divided by open parenthesis n factorial close parenthesis cubed times x to the power of 2n, all divided by open parenthesis 1 minus 2x close parenthesis to the power of 3n plus 1.
Wow, that is one complicated looking formula.
Yeah, it can be a little intimidating, but generating functions like this, they're really useful for figuring out things like how the Franel numbers grow as n gets really big. They can also help us see connections between the Franel numbers and other well-known functions, and they can be used to figure out all kinds of identities involving the sequence. The OEIS entry even mentions a connection to hypergeometric functions, which are a really general class of special functions that show up all over math. They have deep connections to differential equations, too.
So there's a lot of information packed into that one generating function. But I also noticed that there's another one listed that's a little less intimidating looking.
Yeah, that one's a little bit more elegant. It says that the sum for n greater than or equal to 0 of n times x to the n, all divided by open parenthesis n factorial close parenthesis cubed equals, and then the whole thing is squared, open bracket, the sum for n greater than or equal to 0 of x to the n divided by open parenthesis n factorial close parenthesis cubed, close bracket, squared. It's a little bit hard to say out loud, but it's a pretty cool equation.
It is cool and a lot more compact than that first one. And I also saw something in the outline about a differential equation.
Yeah, so the generating function for the Franel numbers, it satisfies a particular linear differential equation with polynomial coefficients. It's kind of a mouthful, but what it means is that the generating function belongs to this special class of functions called definite functions. These functions, their derivatives, they span a finite dimensional vector space over the field of rational functions. And that differential equation can be used to study the analytic properties of the Franel numbers.
So it seems that we have a whole bunch of different ways to look at these Franel numbers. We have the explicit sum, the recurrence relation, and now these generating functions, and even a differential equation. It's really amazing how all these different ideas are connected. So now let's move on to something that sounds pretty cool, connections to other mathematical objects. The outline mentions a connection to algebraic geometry, which seems pretty surprising.
Algebraic geometry. Yeah, that one's pretty wild. So the OEIS entry mentions this connection to a specific point on a curve that was described by an algebraic geometer named Arnaud Bouville. What this means is that it's possible that Franel numbers have some kind of geometric interpretation, maybe something to do with counting points on certain algebraic varieties. It's pretty advanced stuff, but it's incredible that a sequence that comes from combinatorics can show up in such a complicated field like algebraic geometry.
Wow, I never would have guessed that. Now, what about this connection to polynomial algebra?
Polynomial algebra, yeah, that one's really cool. It says that the nth Franel number, a of n, is equal to the constant term in the expansion of this polynomial. Open parenthesis, 1 plus x, close parenthesis, times, open parenthesis, 1 plus y, close parenthesis, plus open parenthesis, 1 plus 1 divided by x, close parenthesis, times, open parenthesis, 1 plus 1 divided by y, close parenthesis, all to the power of n.
So that's another way to define the Franel numbers, but this time using polynomials instead of binomial coefficients.
Exactly.
And there's a connection to Legendre polynomials too, right?
Legendre polynomials, right. So these are really important in lots of areas of math and physics. It turns out that the nth Franel number, a of n, it's the coefficient of x to the n in the expansion of this expression. Open parenthesis, 1 minus x squared, close parenthesis, to the power of n, times the nth Legendre polynomial p of n, comma, open parenthesis, 1 plus x divided by 1 minus x, close parenthesis.
Wow, it's really remarkable how these Franel numbers keep showing up in so many different areas of math. What about integral representations?
Yeah, Franel numbers also have integral representations, which means we can write them as integrals. These integrals often involve trigonometric functions, and they can give us some really cool ways to study the sequence.
And I think there was also something about them being diagonals of rational functions, right?
Diagonals of rational functions, right? So this is a pretty abstract concept, but basically the diagonal of a multivariate rational function is a sequence that's formed from the coefficients where the exponents of all the variables are the same. And it turns out that you can get Franel numbers as diagonals of specific rational functions. It's a pretty deep result that has connections to the theory of definite functions and generating functions.
Okay, and last but not least, there's an identity mentioned in the outline that involves sums of cubes of binomial coefficients, but with shifted indices. What's that about?
Right, so this identity tells us that if you have a non-negative integer r, then the sum from k equals r to n of open parenthesis k choose r, close parenthesis, cubed times open parenthesis n choose k, close parenthesis, cubed is equal to open parenthesis n choose r, close parenthesis, cubed times a of n minus r.
So yet another connection between binomial coefficients and Franel numbers. It seems like no matter where we look, we keep running into them. Now, I know these are called Franel numbers, so there must be some historical context there. Who was Franel?
So Jerome Franel was a Swiss mathematician. He lived from 1859 to 1939. He was the first one to study these numbers, and he wrote about them in this journal called Intermédiaire des mathématiciens back in 1894. So these numbers have been around for over 100 years, and people are still discovering new things about them.
It really is incredible how much there is to discover about these seemingly simple numbers. Now, for any listeners out there who might want to do some exploring of their own, does the OEIS entry have any resources that could help them out?
Yeah, the OEIS entry has some great stuff. It includes code snippets for different computational algebra systems like Maple, Mathematica, ParyGP, Haskell, and Sage. These tools let you calculate terms of the sequence really easily. You can play around with it and see what patterns you can find. You can even check some of the identities and formulas we talked about.
Awesome. Well, we've covered a lot of ground today. We talked about how Franel numbers are defined, about Strel's identity, and we saw how they pop up in different areas like game theory and the study of semi-magic squares. We talked about recurrence relations, prime numbers, and these really cool things called Apery-like sequences. And we dove into generating functions and their connections to other mathematical objects. I have to say, it's pretty amazing how much depth there is to these numbers.
It really is. You know, we started with this simple idea, a sum of cubed binomial coefficients. But that simple idea led us to all these different areas of math, from algebraic geometry to polynomial algebra. It really shows you how interconnected math is and how even the simplest things can lead to some really deep discoveries.
Absolutely. So for our listeners out there, if you're interested in learning more, I definitely recommend checking out the OEIS entry for A00172. There's a ton of information there, formulas, identities, references to research papers. You could try playing around with the generating functions, or maybe see if you can program that recurrence relation. There's a lot to explore.
And as you're exploring, maybe ask yourself, what other simple formulas out there might have these kinds of hidden connections? What other surprising relationships might be waiting to be discovered in math? There's a whole world of math out there just waiting for someone to explore it.
It's a great question to ponder. Well, that's all the time we have for today. Thanks for joining us for this deep dive into Franel numbers. Until next time, keep those mathematical minds working.